All right, welcome to another calculus video in which I can't say words correctly and I breathe too heavy. Calculus. All right, today we are looking at section 5.2, which is about the definite integral. Why can't I speak? Anyway, if f is a function defined on a closed interval a to b, and we divide the interval a to b into n equal subintervals, sound familiar? We just did this last class, with points in between a and b, such that all of these values are any sample points in each subinterval, and delta x is equal to b minus a over n. Then the definite, why can't I spell today? Definite, there we go. Then the definite integral of f from a to b is given by this notation. So we have this integral. It's like a tall S, okay? And it goes from a to b. This is my lower limit, my upper limit of f of x dx is equal to that limit that we peeked at last time, where you've got the limit as n approaches infinity of the summation as I goes from 1 to n of f of x sub I times delta x, as long as it exists. Now, in the above definition, the summation of the limit as n approaches infinity as I goes from 1 to n of f of x sub I times delta x is called the Riemann sum, after the German mathematician Bernhard Riemann, who waxed lyrical on it. Let's take a look at some examples. So let's express this limit as a definite integral on the given interval. Okay, so remember, the integral looks like this. A to b of f of x, sorry, no sub I, that's for the limit notation, for f of x times d of x. All right, so if we look at this whole thing right here is replaced by the big S. These pieces right here, this is A and this is B. This piece right here, that's my function, but I'm not going to use a funky x sub I. I'm just going to use a regular x. And then I'm going to replace delta x with dx. And that's it. Now try it with the next one. Okay, remember, this thing gets replaced with what? Good, the summation. These are the limits of integration. We start off with the small pi and go to the big 2 pi. Next, we're going to put this one in without the x sub I, so it becomes cosine of x over x. And then we replace the delta x with the dx. Here are the parts of the definite integral. The function that's to be integrated is called the integrand. When we say dx here, this tells us that which variable we're taking the integration of. B is your upper limit. This is our integral sign. A is our lower limit. And then we just basically call this whole thing the integral of f from a to b. Now, the definite integral is a value, okay? As long as we have those values of a to b, that means our answer is going to be a number. We're not going to get an equation out of it. So it's a value and doesn't depend on the variable x. So we can use other variables in place of x. So like, let's say I'm dealing with f of t. So I would do f of t dt, and then t goes from a to b. Well, let's say I wanted to do z. So I would do f of z dz, and I would do it as z goes from a to b. Let's pick another variable. How about p? F of p dp, and then not that, and then as p goes from a to b. Yeah, so we can write it quite a few ways. All right, I talked last section about left endpoints and right endpoints, and what I did not yet talk about are midpoints. So we're going to look at the midpoints rule with the Riemann sum. So instead of using, I don't know if you remember before, we either would use, the right hand or the left hand to find the height of something, or we'd use the right hand to find the height of something. But what if we did it with midpoints? So midpoints would be the heights are determined by the midpoints of the interval. So this thing right here, this is called x sub I, or sorry, x bar sub I. That bar over the top, that means average. The midpoint is an average. So this is x bar sub I. And this is the midpoint of an interval. So it's the midpoint of any interval between x sub I and the one below it. So again, delta x is just going to be that b minus a over n, and x bar sub I is going to be equal to the sum of the interval divided by 2. Okay. And then if I'm trying to find this, I'm just using the x bar value in there. So it would be delta x times f of x bar 1 plus f of x bar 2 plus blah, 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 all the way to f of x bar n. So let's use the midpoint rule with n equals 4 to approximate this integral. So it's n equals 4. So we need to do 4 values. So a is 1 and b is 5. Okay, so a is 1 and b is 5. So first things first is, I put like a little number line down just to kind of visualize the area, especially the values I'm going to use. You find your delta x and your sample value. So delta x, remember, is b minus a over n. So this is going to be 5 minus 1 over 4, which is going to be 4 over 4, which is 1. So here are going to be my subintervals. So they're width of 1. 1, 2, 3, 4. Wait, 1, 2, 3, 4, 5. Yeah. Sorry. Bad drawing. Space this out a little bit more too. Oh. No, that was me making noises while erasing. Sorry, my dog wants to talk to you guys. Shh, please. All right, here's the deal though. These are not the midpoints. These are the end values of the subinterval. So I have to do the midpoints. So now, I need to find the midpoints. So basically, for the first interval, if I were to find the midpoint here, right, what's the midpoint? I'm going to take 1, plus 2 divided by 2. So this is going to give me 3/2 or 1/2. I mean, but we know that. So my point here is going to be 1.5. And then the halfway mark between 2 and 3. And again, if I didn't know that it was going to be 2.5, I would just take 2 plus 3 divided by 2, which would give me 5/2, which is 2.5, and so on and so forth. All right, but let's write down all the midpoints. The other thing is make sure that when you calculate your midpoints that they are delta x away from each other, and they are. From 1.5 to 2.5 is a distance of 1. All right, now we're going to do the formula. So we're going to do the plug and chug. So we are approximating. So from 1 to 5 of x squared e to the negative x dx, what we're going to do is we're going to do the sum of all the values, remember? So we've got delta x is going to go in first, and that's 1. Next, I'm doing the sum of my outputs. So I do f of 1.5 plus f of 2.5 plus f of 3.5 plus f of 4.5. And I've got 1, 2, 3, 4 in 4 subintervals. And then I evaluate it. All right, this one's going to be a little messy because I've got e in there. So just round your final answer to a couple of decimal places. The long drawn out value is 1.6099492229, blah, blah, blah. But if I round that to a couple of decimal points, I got 1.61. And that's my value to approximate the integral. All right, now let's look at this one. Here, they want us to express the integral as a limit of the Riemann sum, but they don't want us to compute the limit. So let's do that. So, first things first is remember what goes into all the pieces, right? So the limit, first of all, we're going to have the limit as n approaches infinity. We're going to do the summation as I goes from 1 to n. And then in here, we're going to put our f of x sub I. And then over here, we're going to put our delta x. So first things first, find that delta x. So it's b minus a over n. So 4 minus 0 over n, which is going to give us 4 over n. Next, we find our x sub I. So it starts with a, which is 0. And then I'm going to add to it my delta x, which is 4 over n times I. So this is just going to be 4 nths I. Next, I'm just plugging and chugging. All right. So I'm going to have over here, I'm going to plug in 2 times my x sub I. So 2 times my x sub I is going to be 2 times 4 over n I. And then down at the bottom, I have 1 plus x squared. That's going to be 1 plus x sub I squared, and then times delta x. And then that's it. I mean, I might want to simplify a little bit, but really that's it. They didn't want us to compute the limit, so I don't necessarily know that they want us to simplify it either. I might just do a little cleaning house here, like write this as, well, I'm going to leave the 2 on the top, but I'm going to bring this one down here. So I'm going to have 2, 1 plus, should I square it? I don't know. I'm gonna. And then I've got the 2 here times 4, so 16 times 2, so 32. And then I have I, and then I'm going to have another n. That's going to be in the bottom, though. That looks like garbage. No, I'm not going to do that. We're just going to leave it. The only thing I'm going to do is on the top, I'll just write this. And again, it's just because I'm not evaluating it. You know, my math brain, my teacher brain wants to simplify. Thou shalt simplify. It's a compulsion. All right, but that's good. Next, let's look at the definite area under a curve. So if I've got this value here, f is continuous and positive, so in other words, f of x is greater than 0, and it's on a closed interval ab, then this integral of f of x from a to b can really be thought of as the area under the curve of f of x from a to b. So in general, the definite integral can be interpreted as the difference of areas, where this a positive is the total area of the regions above the x-axis, and a negative is the total area of the regions below the x-axis. So if I'm looking at something, here's some function, and here's my lower limit a and my upper limit b. And if I wanted to figure out these areas under the curve, the ones above the x-axis, those are positive areas. And the ones below the x-axis, those are negative areas. And doesn't it make sense? Like if I have a little rectangle down here, that y value, that height, that's going to be negative. Same thing here. If I have a little rectangle up here, that height of the rectangle, that's going to be positive, right? Okay, let's look at some examples. So we're going to start off with some things that we could easily find the area of, right? So notice for letter A, we've got something that we can easily graph and then find the area of. For letter B, they didn't even tell us what the function is. They just gave us the graph. All right, so first thing we need to do is we need to graph the line x minus 1. So minus 1, and then x has a positive slope of 1. And then this is our whole function. So we're going to graph and connect the dots. All right, we're doing this from x equals 0, which is right here, this point, to x equals 3. So 1, 2, 3. So we're looking at the area under the curve. And so that's going to be this area here, because this is my 0. And then this is my 3, and the area right there. Well, that's going to equal those areas, so I just need to find that little tiny area of that triangle, and then find the slightly bigger area of this triangle. All right, notice that this little triangle here has a height of -1 and a base of 1. So for the area of that little triangle, I'm going to have 1/2 base times height. And then here, if I look, I've got a base of 2 with a height of 2 as well. So plus 1/2 times 2 times 2. If I combine those and get them all together, I'm going to have -1/2 plus 2, which is going to give me 3/2. Now for the next one, I'm going from -5 to 5. So here's -1, 2, 3, 4, 5. So here's -5. And so I'm finding this area under the curve. And then I'm going all the way to +1, 2, 3, 4, 5. So then I'm finding this area under the curve. And then this area under the curve. So I'm finding this, you know, this bigger triangle plus the area of half a circle plus the area of this smaller triangle, right? Okay, so let's label the side lengths here so we can do some mathematics with it. All right, so from here to here, this is 3. From here to here, this is 1, 2, 3, 4, 5, 6. Okay. And then if I look at the circle, the measurement I need is a radius, and it has a radius of 2. And then for this triangle, I've got a base of 3 and a height of 2. So for this first triangle here, I'm going to have 1/2, 3 times 6, and then plus, and then 1/2 times pi r squared, and then plus 1/2 times 3 times 5. And if I evaluate that for something exact, I can say, okay, that's like saying -5.5 minus 2 pi, or I could say it's a -10.78, depending on whether or not they're asking for an exact value or for a decimal approximation. Now, there are some properties of integration I'd love you to pay attention to because we're going to use them. All right, first of all, if you flip the limits of integration, it makes it negative. So if this one goes, notice this one goes from B to A. If I flip it and go from A to B, I have to switch the sign. And if I do the limit from A to A, that's going to be 0. Because remember, these are areas between values. And the values have to be far apart in order to have some type of width. If you're just trying to find the area under the curve at A, well, that has no width. So that's going to be 0. Here, if you're just doing the integral of just a constant, it's going to be c times b minus a. Here, if you've got the constant in the function, you just move that constant out. Here, if you're going to add integrals, you can just add or subtract the integrals if you have 2 of them. Say you have things separated by terms. And then I always think that this one's pretty neat because it's helpful to find certain areas. If you know that C is in between A and B, then the integral of A to C of f of x plus the integral of C to B is going to give you the integral all the way from A to B. So in other words, you can kind of smush it up. Okay, again, you can go from A to C and add to it C to B, and that'll get you all the way from A to B. It's like skipping the middleman, C. Next, if your function is positive in that interval, then your integral is also going to be positive, right? If it's above the x-axis, it's positive. And then same thing here. If you have f of x is larger than g of x for all x values in this interval, then their integrals are also going to be larger, right? If something is taller, same width, if something is taller with the same width, it's going to have a bigger height and therefore a bigger area. And then for this one, if I've got f of x falls in between these values of lowercase m and uppercase m for all x and b, then I can say the integral of f of x from m to b, or from a to b, sorry, goes from lowercase m times b minus a to uppercase m times b minus a. All right, well, let's apply those. Let's apply those. We got a bunch of rules. So I am going to do this function here. I want to find the integral of g of x from 1 to 5. And I look at what I have, okay? So I've got the integral of f of x from 1 to 2. The integral of f of x from 1 to 5. Neither of these are help me. I need g. Next, I've got an interval of g of x from 1 to 5. Well, this is from 5 to 1. So this would be like saying it's the exact same as the negative of the integral from 1 to 5 of g of x. So it would be a negative value that they gave us, which would be 8. All right, for this one, I've got the integral of f of x goes from 1 to 2, multiplying it by 3. Remember that 3 can come out. So I really just need to figure out what the integral of f of x is from 1 to 2 and then multiply it by 3. Well, they gave me that fact. That's this fact right here. So that's going to be 3 times negative 4, which is going to give me negative 12. All right, next. For f of x, as it goes from 2 to 5, the integral with respect to x, let's take a look. So I want to know 2 to 5. Do I have any information that gives me 2 to 5? All right, well, no, I don't. But let's see what I have for f of x. So I do have from 1 to 2 of f of x. And I also have 1 to 5 of f of x. Let's think about those properties. Well, first of all, let's kind of look at this. Who's bigger, from 1 to 2 or 1 to 5? Yeah, if something's wider, it's bigger. So I need to have something over here. Now, if you remember those properties, if I go from 1 to 2, I can get to 5 if I put the number 2 down here. And that's where the magic is. So let's do that. So from 1 to 2, f of x, this is going to give me negative 4. This one, I don't know what it is. Let's just call it w. And then 1 to 5, we know is 6. So I just need to add 4 to both sides. And I get this value to be a positive 10. Next, I just need to subtract these and move the 4 out. No, not that. So I'm going to take this integral and I'm going to smush it in between the 4 and the fx, and then I'm going to put it in front of the g of x. So I'm going to have 4 times the integral from 1 to 5 of f of x. And I'm going to make sure everybody gets a dx too. I'm going to minus the integral from 1 to 5 of gx dx. And then I'm just going to plug those values in. So 4 times the integral of f of x of 1 to 5 is going to be 4 times 6 minus, and then this one's going to give me 8. So 24 minus 8, and that's going to give me 16. All right, I hope that made sense. If it doesn't, of course, you can always watch it again or come to office hours. Enjoy.